in this module we will be discussing special functions and curvilinear coordinates. So, there are several functions which we use during various applications which fall in the category of what are called as special functions, and there are different reasons why these are special. We will be looking at some of these special functions during this module. The first special function that I want to talk about and which will be discussed in this lecture is the step function and its derivative, which is a delta function. So, before I get into the step function and the delta function, let me introduce you to a way of thinking about functions. So, whenever you have a function, okay, it is very useful to think of the graph of the function. So, think of the functions in terms of graphs, or plots, and this idea is extremely important, and it will really help you understand the behavior of functions a lot more. So, whenever you see any function, it is a good idea to plot the function. So, suppose you have for example, if you have sin x, then when you plot it, you know that it will look as a function of x. You will plot you'll plot sin x, and you immediately know that it will have this sort of behavior. It will be periodic and it will be oscillating, and you know that the period is 2 pi. So, it will go, and then it is an odd function. So, you will see that it goes the other way on the other side. So, this is minus pi minus 2 pi, and also you know that the amplitude is equal to 1. Its maximum value is 1 and its minimum value is minus 1. So, you think of the function in terms of the graph. Now suppose on the other hand you had a function like let us say x square. So, x square, you know that what will happen is that x square will start at 0, it will always be positive, and it will keep increasing higher and higher. Okay. So, unlike sin x, which is oscillatory, x square is something that will just keep increasing. Okay. So, that is what x square looks like, the graph in blue, and sin x looks like this. Okay. Now these are, so it is always very useful to plot functions, and what I will be doing during this course is to say that if you have some arbitrary function, okay, then it will have some graph. And you know, you can just show it as some graph. Okay. Now, what is important about the graph is that for each value of x, there should be only one value of the function. So, you cannot have a graph that looks like this. This is not possible because for this value of x, this is not a function, because it does not have a single value. So, suppose you ask what is the value of the function here, it can be either this or this or this. Okay. So, it becomes multi-valued here, and in general we do not talk of this as a function. So, the other thing is now you can have a graph, and what more, you can have functions where the graph is not continuous. So, you could have a function that looks like this, and then goes like this, and then goes like this. So, you could have a function that looks like this. Okay. So, it is discontinuous in this point. So, all these are examples. So it is very important that you should get a sense of what the function does just by looking at the graph. Okay. And arbitrary functions will have some graph, okay, and which will have some features which we can analyze. Okay. So, now let us come to the step function. So I will call it the unit step function. Okay, and I will call this h of x, okay, and h of x is defined, it is equal to 0 if x is less than equal to 0 and is equal to 1 if x is greater than 0. Okay. So, what you notice just from the definition of the function, you notice that that at x equal to 0 there is a discontinuity. Okay. And now we can make a plot of this function. So, the plot of this function will look like this. So, let me show it in blue. Okay. So, the plot of the function will be 0 for all values of x less than 0. So, it is 0 along this axis, then it at x equal to 0 it goes to 1 and then it stays at 1. Okay. This value is 1. Okay. So, this is what your function looks like. This is x, this is h of x. Incidentally, this function is also called the Heaviside function. Okay, Heaviside was a mathematician. Okay, so it is named after him, and so the Heaviside function is has this feature that it is 0 for x less than 0 and is equal to 1 if x is greater than 0. Now, you could also have step functions which are slightly modified versions of step functions. For example, instead of, you could have h of, let us say, x minus a. So, what will h of x minus a look like? So, it is a Heaviside function of x minus a. Okay. So, what this will look like is the following. So, it will be 0 when x minus a is less than 0, that is x is less than a, and let us say a is this value, this is x equal to a, and it is 1 when x is greater than a. Okay. So, this is Heaviside function of x minus a. Okay. This Heaviside function is actually so Heaviside function or unit step function is discontinuous. Okay. Now, you can construct several different versions of this Heaviside function. Now, suppose you want a function that is whose amplitude is not 1, but it is something else. Okay. So, what you can do is you can multiply by, let us say, b, capital B h of x minus a. Okay. So, this will look like a Heaviside function, okay, whose amplitude which is 0 all the way until x equal to a, and whose amplitude is b. So, this amplitude equal to b. Okay. So, you can actually manipulate Heaviside functions to get various kinds of Heaviside functions. You need not have just amplitude 1, and you need not have only the discontinuity at x equal to 0. So, you can change the location of the discontinuity and you can change the amplitude. Okay. You will get different functions which are also step functions, which are not unit step functions, okay, but they are sort of slightly modified step functions. Now, you could also have a Heaviside function which is suppose you take minus of, I will just say, b times h of x minus a. Okay. So, suppose I take minus of b times h minus h of x minus a, and I will show this in red. So, that will look, it will be 0 and then it will go to minus. Okay. And this value is minus b. Okay. So, I could have this is minus b h of x minus a. Yeah. Now, I could do lot of other things. I could let us say if I add these two functions, of course I will get 0, okay, but I can do things like let us say I consider a function that has this form. So, let us say I say a1 h of x minus a1 plus or let me put a minus sign here just to minus a2 h of x minus a2. Okay. So, what will this function look like? So, if you take this function, okay, and let me I'll draw each of the functions. So, I haven't explicitly told you the values of small a1 and capital A1 and small a2 and capital A2, but you know whatever their values are, we will plot the functions based on their values. So, let us say this is let us assume this is a1, okay. Then what you have is you have it coming off, you have it 0 all the way to a1, the first function. So, this is first function and this is the second function, okay. So, the first function will be 0 up to here, then it will go all the way to a1, okay. The second function, let me say it goes so this is the first function. The second function, let us say it goes 0 all the way up to a2 and then it goes up all the way to a2, okay. This is the second function, okay. Now, if you take the difference of these two, okay, if you take the difference of these two, okay, then you can see what will happen is that in this region they both are 0. So, their difference is 0. In this region you will just have a1 because the second function is still 0. So, all the way up to here you will have the same. So, let me show this in green, okay, just to show you what the difference looks like. So, it follows this graph, okay, and then it goes here and then it goes along this. Now, what happens at this value? At this point you have the value becomes equal to a1 minus a2. So, it goes a1 minus a2 and I have shown a2 greater than a1. So, a1 minus a2 will actually be negative. So, it will go to something like this and it will go, it will stay at this value of, so this value is a1 minus a2, okay. A1 minus a2 is less than 0 and that is what the value will be, okay. So, what we got through this exercise, we got a function and I will make it in dark now, yes. So, we got a function that looks like this, okay. So, by basically adding and subtracting Heaviside functions, we can get functions that look like you know that are non-zero for some value. You can get all kinds of functions by this. So, essentially I will just conclude the discussion of step functions right here. So, you can get functions that look like, you know, you might get something like this. You might have a function that looks like this. You can get a function that looks like this by combining step functions, okay. So, suitable combinations of step functions can give you all kinds of shapes, okay, and some of those are fairly useful in various calculations, okay. Now, the next, so now we said that the step function, so h of x, okay, equal to 1 if x is greater than equal to 0, equal to 0 if x is less than 0, okay. Now, the exact value at 0 is debatable. So, you can it jumps from 0 to 1, okay. Now suppose I take d by dx of h of x. Okay. So clearly if x is greater than 0, okay, the derivative is 0 because the function is constant. Okay. If x is greater than 0, equal to 0 if x is less than 0. Okay. So now again you go to our graph, okay, and you see what happens. So what you have is you had your step function, your unit step function. Okay. So this is h of x. Okay. Now you are taking the derivative of this. Okay. Now if you take the derivative, okay, clearly it is 0 here because the graph, since the derivative is nothing but the slope of this curve, and so since the curve is flat, your derivative is 0 here, your derivative is 0 here. Okay. Now what about right at x equal to 0? At x equal to 0, your change of the function, your function changes by by 1 unit over essentially no interval. So over an infinitesimally small interval, it jumps from 0 to 1. So the derivative has to be equal to infinity here. So right here your derivative becomes infinity because it is changing very rapidly. Okay. And I have exaggerated, but basically your derivative, if you I made a small mistake here. So the derivative is actually 0 here. So your step function, the derivative is 0 here, it is 0 on the right. Okay. The function has value 1. Okay. Your function has value 1, but the derivative is actually 0. Okay. So your function has value 1, the derivative is 0 on this side. Okay. So your derivative looks like this. So it is 0 here, it is 0 here, and it has a big jump here. So equal to infinity at x equal to 0. Okay. Now let me call this function in red, I will call it as a, it is known as a Dirac delta function. Or simply a delta function sometimes. Okay. And it is denoted by the symbol delta of x. Okay. So what does delta of x look like? Delta of x, if I plot it, then it just looks, it is 0 everywhere and it has a spike here and again it is 0. So it is sometimes called a spike function. Now what is the feature of this delta function? So suppose you integrate over the delta function. Okay. Integration is the opposite of differentiation. So if you integrate over delta of x dx from, let us say 0 to a, okay, what you will get is exactly h of a. Okay. So that is equal to 0 if x is, if a is less than 0, equal to 1 if a is greater than equal to 0. Okay. So the integral will be 0 all the way here because your function is 0 everywhere. Then just when you cross this, your integral will go to 1, and then once it goes past this, your integral will always be 1. Okay. So what that means? So if you look at integral from, I should say minus infinity, from minus infinity. So this is minus infinity to plus infinity. So integral from minus infinity to plus infinity delta of x dx. Okay. Now a is greater than 1, a is greater than 0, so it is equal to 1. Okay. So the delta function has this feature that its integral is 1. So delta, so the Dirac delta function has unit area. Okay. There is one more feature of the Dirac delta function which makes it really useful is the following. Suppose I take f of x multiplied by delta of, and let me say x minus a dx, and I integrate it from minus infinity to plus infinity. Okay. This will give me exactly f of a. Okay. So what did I do here? So I have I can show this pictorially. So you have let me show it in red. So let us say I have f of x, this is f of x, okay, and I multiplied it by a delta function delta of x minus a. So now delta of x minus a will give me a spike at x equal to a. So this is delta of x minus a. Incidentally, I didn't go through this detail, but basically delta of x gives the spike at x equal to 0, delta of x minus a will give me the spike exactly at x equal to a. Okay. So the infinite spike that you get will be at x equal to a. Okay. And now when you multiply these two, okay, then what you will get is essentially this value of the function. This is f of a. Okay. So what you will get is this will be 0 unless x equal to a, and at x equal to a you can replace f of x by f of a. So you just get f of a. Okay. So just to work this out, you can do it, you can think of this the following way. So this is integral minus infinity to plus infinity f of a times delta of x minus a dx, and since f of a is because this is 0 unless x equal to a. So this product is 0 unless x equal to a. Okay. So I just take f of a outside, so I can write f of a, and what I am left with is integral of a Dirac delta function which is equal to 1. So I just get equal to f of a, and this is sometimes used as the definition of the Dirac delta function. So basically so the Dirac delta function, okay, you can think of as having two features. Okay. So the Dirac delta function, so what we so if you take any continuous function f of x satisfies integral f of x delta of x minus a equal to f of a from minus infinity to plus infinity dx. Okay. So any continuous function will satisfy this. Okay. Further you have integral minus infinity to plus infinity delta of x. So if I just put a 1, you can think of this as just putting a 1, instead you can just think of f of x equal to 1. So f of a will also be 1. So this is equal to 1. Okay. So you can use this as a definition of the delta function. So any function that satisfies this for any arbitrary f. So if you have that will be called a Dirac delta function. So this is sometimes used as a definition of Dirac delta function. Okay. So a Dirac delta function is essentially always defined only under the integral. Okay. So this is a function that is only defined under the integral. You don't write Dirac delta functions without the integral. So you cannot evaluate. If you ask what is the value at x equal to a of the Dirac delta function, you cannot say it. Okay. But it is perfectly well defined under the integral. Okay. So I will conclude this lecture here. Okay. So, in the next lecture we will look at other special functions.